So, picture this. It's the morning of April 17th, 2013, and the prestigious journal Annals of Mathematics gets a really weird email. Attached is a 50-page mathematical proof making an absolutely massive claim. It essentially claimed to solve a piece of one of the oldest, most notoriously unsolvable problems in math history. We're talking about a problem the legendary mathematician Edmund Landau once literally called unattackable. But, the real mystery here wasn't even the math itself. It was the sender. This proof didn't come from some hotshot tenured professor at Harvard or Oxford. It came from a total, absolute unknown.
The guy behind the email was a man named Yitang Zhang. And his story? It's wild. After getting his PhD, Zhang couldn't secure a single recommendation letter. Zero. He struggled so much to find academic work that he actually ended up living in his car for a bit, working odd jobs for 7 whole years. He was even working at a local Subway restaurant, just keeping the books and sorting receipts. But, get this, while he was doing all of that, in his spare time, he'd quietly drive down to the local library just to read number theory journals. He was grinding away on this impossible math problem in total, complete isolation.
Right. So when the journal editors opened this 50-page paper, their very first thought was, okay, yeah, there is no way this is actually going to work. They sent it off to their top-tier referees, fully expecting them to spot a fatal flaw by, lunch. But they didn't. These reviewers painstakingly combed through all the incredibly fragile parts where proofs like this usually just fall apart. They kept flipping the pages, waiting to hit a dead end, but every single time, Zhang had cut the mathematical corners flawlessly. By the end of the week, the sheer shock really set in. One of the reviewers summed it up perfectly. Oh, damn, he did it.
Part 1. The twin prime conjecture. To really grasp what he pulled off, we have to meet the ancient mathematical villain he was up against.
So, what exactly are twin primes? Well, they're just prime numbers separated by a single even number. Think 11 and 13, or 17 and 19. Now, the big rule with prime numbers is that as you count higher and higher up the number line, they get rarer. The average gap between primes grows roughly like the natural logarithm of the number. It's a slow growth, but it literally goes to infinity. So, finding primes that are just 2 digits apart gets insanely difficult. But the twin prime conjecture? It boldly claims that no matter how far out you go, you will absolutely never run out of these twin primes, that there are infinitely many of them.
Just to give you a sense of the sheer scale we're dealing with here, 388,342. That is the number of digits in the largest twin prime pair we have physically found so far using computers. If you were to print just one of those numbers in a normal book, it would take up about 260 pages. And sure, we keep finding them the further out we look, but empirical counting isn't a mathematical proof. We obviously can't physically check numbers out to infinity. For that, we need an airtight, rigorous proof.
Part 2. The error term problem. Because to get that airtight proof, mathematicians had to build a specific kind of mathematical machine, and they quickly hit a massive roadblock.
Okay, let's rewind a bit. Over 100 years ago, right in the middle of the First World War, a 29-year-old Norwegian mathematician named Viggo Brun tried to solve this exact problem on his own. He dusted off a 2,000-year-old tool called the sieve of Eratosthenes. The logic is actually pretty simple. You circle a prime, like 2, and cross out all its multiples. Then you circle 3, cross out its multiples, and so on. Whatever survives the sieve, those are your prime numbers. Brun wanted to adapt this ancient sieve to specifically count the twin primes left over.
But here's where Brun ran into an absolute arithmetic nightmare. See, when you cross out multiples of 2, 3, and 5, some numbers get crossed out twice or even 3 times. To get the actual true count, you have to add back those overlaps and then subtract the triple overlaps. Mathematicians call this inclusion-exclusion. And this right here brings us to the core boss battle of analytic number theory, the fight between the main term and the error term. As you sieve by more and more primes, your rounding errors just multiply exponentially. For twin primes, these errors grow roughly like 4 to the power of k. So very, very quickly, these error terms violently explode, completely swallowing up the main predictable calculation.
Because of this, Brun had to make a really tough compromise. To stop those exploding errors from just completely ruining the math, he had to intentionally weaken his sieve. Instead of sieving all the way to the square root of his target number, he only sieved up to the power of 1/10. Now, he did successfully get control of the error terms, which is great, but the massive catch was that his weakened sieve let a bunch of imposter primes slip right on through. The absolute best he could prove is that there are infinitely many pairs separated by 2 where the numbers have a maximum of 9 prime factors, so not pure primes. And with that, the entire mathematical world was just stuck. Part 3. The Stencil Method Wall. After decades of chipping away at this and getting nowhere near pure primes, mathematicians completely flipped the script. Enter a team of mathematicians known as GPY. They decided, hey, instead of trying to count twin primes directly, let's just try to prove that primes stay close together. So they built this sort of theoretical averaging machine using a stencil. Picture it like this. You take a theoretical stencil with specific holes cut out, and you slide it over a range of numbers on a number line. You peek through the holes, count how many primes you see, shift the stencil over, and repeat. At the end of it all, you calculate the weighted average of how many primes your stencil managed to catch per position.
The logic behind this averaging machine is honestly just beautiful. Their ultimate goal was super straightforward. Get the average number of primes per position to be strictly above 1. Why? Because if the average across the entire number line is greater than 1, the math guarantees that at least one placement of that stencil caught 2 primes at the exact same time. And if you can mathematically prove that this holds true even as numbers stretch out to infinity, boom, you've proven that primes are infinitely bound by whatever the width of your stencil is.
But of course, there's a catch. To make this brilliant machine actually work, the GPY team had to properly weight their stencil. And doing that meant they needed to know exactly how primes are distributed across different step sizes. They had to rely on a specific theorem from the 1960s, but that theorem had a hard ceiling. Experts call it the 1/2 barrier. In 2005, literally the top mathematical minds in the world gathered at the AIM conference out in California just to try and push past this very barrier. They spent a whole week trying to force their machine's average above 1, but they couldn't. They slammed right into that 1/2 wall, and collectively, they deemed the problem completely impossible.
Part 4. Zhang shatters the barrier. The world's top experts threw in the towel. But remember, a certain someone was not at that 2005 conference.
Yitang Zhang had absolutely no idea that the establishment had given up. He spent years just quietly internalizing this whole GPI argument. And then, during a summer trip to Colorado in 2012, literally while pacing around a friend's backyard waiting for deer, the breakthrough hit him. You know where the GPI team got totally stuck at that 1/2 distribution barrier? Well, Zhang realized that if he specifically focused on step sizes built only from really small prime factors, he could reorganize those incredibly nasty error terms so that most of them just canceled each other out. He managed to push past the supposedly impossible 1/2 barrier by a microscopic fraction. We're talking just 1/584.
But hey, that tiny little fraction was all he needed. By inching past that barrier, his mathematical averaging machine actually worked. Zhang officially, rigorously proved that there are infinitely many pairs of prime numbers separated by no more than 70 million. He had proven a bounded gap. The impossible was actually done. Literally overnight, this obscure former subway worker became an absolute mathematical hero and ended up winning a MacArthur Genius Grant.
Part 5. The Race to 246. Because once Zhang broke the seal and showed everyone that a bounded gap wasn't just some pipe dream, an absolute frenzy kicked off.
It was exactly like the 4-minute mile. As soon as people knew it could be done, everybody jumped in. The brilliant Terence Tao spearheaded this massive online collaboration called the Polymath Group. You had dozens of top-tier mathematicians working together around the clock to optimize Zhang's 70 million gap method. Day by day, hour by hour, people were just frantically refreshing their screens as the world record plummeted. By aggressively optimizing all these calculations, they squeezed that gap down from 70 million to just 4,680.
But wait, because simultaneously, over in Montreal, there was this young postdoc named James Maynard working on the exact same problem. And get this, his own advisor explicitly warned him to stop, basically guaranteeing him that he would fail. But Maynard totally ignored the warning. Instead of tweaking Zhang's math, he used a completely new orthogonal approach to the stencil method. And within months, he brought the gap down even further, totally shattering the polymath record and dropping the absolute bound to just 600.
Now, Maynard's method didn't just lower the number, it actually revealed a totally shocking truth about the math itself. Remember that infamous 1/2 barrier that completely halted the world's greatest minds back in 2005? Well, Maynard proved that the 1/2 barrier wasn't even a fundamental limit to begin with. As he called it, it was a pure mirage, a complete red herring. All Maynard's method really required was a stencil with enough slots.
By breaking away from the specific distribution constraints that all the experts had been relying on, he mathematically proved that the invisible wall never truly existed at all.
Realizing that Maynard and Terry Tao were essentially on parallel tracks, the two decided to join forces. By combining Maynard's massive breakthrough with the raw optimization power of Tao's polymath group, they squeezed out absolutely every single drop of mathematical efficiency possible. And they finally landed on the ultimate number, 246. That right there is the current absolute world record. They proved, without a shadow of a doubt, that there are infinitely many pairs of primes that differ by no more than 246.
Now you might be wondering, can we go any lower than that? Well, yeah, but right now, only conditionally. For example, if we assume this incredibly complex, unproven theory called the Elliott-Halberstam conjecture is actually true, Maynard showed the gap would plummet all the way to 12. And if we assume an even stronger version of that conjecture, the polymath group proved it drops to just 6. But as we know in mathematics, assumptions are not proofs. So without relying on any unproven conjectures whatsoever, the hard, absolute, unconditional proof stands firm right at 246. When you really step back from all the massive equations and exploding error terms we've talked about in this explainer, the big overarching theme here is the hidden advantage of isolation. Yitang Zhang managed to crack one of history's hardest puzzles precisely because he wasn't sitting in that room with the world's leading experts back in 2005. He was never infected by the groupthink that loudly declared the problem completely impossible. His distance from the academic establishment is exactly what allowed him to spot a microscopic crack in a wall that everyone else had just walked away from.
So as we wrap up this explainer, I really want to leave you with this one final thought. Yitang Zhang broke a 2,000-year-old mathematical wall simply because nobody successfully convinced him that he couldn't. So what supposedly impossible barriers in our own lives or in science and technology could we completely shatter right now if we just didn't know they were supposed to be impossible? Think about that for a second and keep